This is the 2019 AP Calculus AB FRQ number 1, and it's about fish entering and leaving a lake. It says that fish enter a lake at a rate modeled by the function e, given by e of t is 20 plus 15 times sine of pi over 6 times t. Fish leave the lake at a rate modeled by the function L, given by L of t is 4 plus 2 raised to the point 1 t squared. Both E of t and L of t are measured in fish per hour, and t is measured in hours since midnight. Now, one of the first things that we want to do here is make sure that we recognize that both of these functions are rate functions, fish per hour. So I've got those units identified, and t, the independent variable here, is measured in hours since midnight. The first question, A, is how many fish enter the lake over the 5-hour period from midnight t equals 0 to 5 a.m. t equals 5. Give your answer to the nearest whole number. I'm trying to calculate fish. That means if I have a rate in fish per hour that are entering, and I want to know how many fish, total units of fish, enter the lake over a certain period, I'm going to have to integrate. And I'm going to integrate over the time period specified from 0 to 5 of my function e of t. My function e of t is 20 plus 15 times sine of pi over 6 times t. Now, this is basically a summation, right, with a dt out here. So the units that I'm going to end up with are going to be fish, because this function that I am integrating is fish per hour times dt, which is hours. That's going to give me units of fish. This is a calculator problem, and let's take a look at how we will do this on the TI-84. I've already entered in both functions e of t and L of t. Y1 is e of t, and we can scroll over and make sure that we've got that entered into the calculator properly. I want to do that when I'm taking the test. Make sure that I double check that the function is entered in correctly. Now, what we do as we come back here, we are going to integrate. I'm going to pull this up again and show you how to integrate numerically. I'm going to hit Math and 9. That pulls up my numeric integration function, and I'm integrating from 0 to 5, and I just have to refer to y1. So I can do alpha f4 y1. The variable as I entered it in was x. Hit enter, and indeed we get an answer of 153.458 fish. So the answer here is 153.458 fish. I'm going to round that up to 154 fish. 154 fish enter the lake from t equals 0 to t equals 5. So we've got that taken care of. The next question is, what is the average number of fish that leave the lake per hour over the 5-hour period from midnight 0 to 5? Well, this is also an integration problem, because when we're trying to find an average number of fish, we are going to integrate, but we are going to divide by the time over which we have taken the integral. So this is going to look like this. So the average fish is going to be equal to 1 over t2 minus t1, so 1 over 5 minus 0. We're going to integrate from 0 to 5, and we're going to do this with the L of t function. And so I'm just going to write L of t dt. All right, now let's take stock here of what we're going to get in terms of units. Now, I am looking for an average number of fish per hour. it's asking me fish that leave the lake per hour. Well, this integral right here is going to give me the number of fish that leave. Right, so this is the number of fish leaving. And then what I'm doing is I'm basically going to be dividing this by the time period, 5 hours. So this will give me fish per hour. I'm going to enter this into my calculator exactly as I have it here. I'm going to start off by creating a fraction. So I'm going to say 1 over 5. I'm going to pull up my numeric integration, math 9. I am integrating from 0 to 5. This time though I'm using the y2 function because that is the function for the rate of fish leaving the lake. And so I need to change that to y2. So I'm changing this to y2 and need to put in an x here, and there we go. So 6.059 is what we have. So we're going to enter this in as 6.059. This is, again, fish per hour. I'm going to go ahead and give a statement here so that the grader knows exactly what my answer is. So I am going to say an average of 6.059 fish per hour leave the lake from t equals 0 to t equals 5. The next question is, at what time t from t equals 0 to t equals 8 inclusive is the greatest number of fish in the lake? Justify your answer. Well, what we're going to do here for this problem is I'm going to create a function that represents instantaneous fish in the lake at any time t, because that's the function that I want to maximize. I'm trying to find what the absolute maximum would be from 0 to 8 for that particular function of instantaneous fish. Well, if I were to call that f of t, so f of t is fish in lake at any time t. It's going to be an integral function because the functions that I was given in the problem are rate functions. So what we'll say is that f of t is going to be equal to the initial number of fish in the lake, which would be the f of 0. But then what we're going to do is we are going to integrate, and we're going to integrate e of x minus L of x. And this would be dx. And we're going to integrate from 0 to t. So you give me a t value, I'll plug it in there, and I can calculate the instantaneous number of fish in the lake if, of course, I know what the initial number of fish in the lake are. But, of course, we were not given that. But the whole purpose here is I'm trying to find the maximum value, right, for this particular function. And so the maximum, right, the maximum f of t is going to occur at t equals 0 or t equals 8, right? I have to check the endpoints because that's where the maximum could occur, or where f prime of t is 0, which are called, of course, critical points. All right, well, I can find t of f of 0 and f of 8 straightforward, but let's go ahead and find what f prime of t is, because that's what I'm going to set equal to 0 to find my critical points. Well, the derivative of f of 0 would be 0, it's a constant, and then the integral of e of x minus L of x from 0 to t is just e of t minus L of t. and I am going to set that equal to 0. So therefore, my critical points are where E of t is equal to L of t. I'm going to determine where E of t equals L of t graphically. On my TI-84, I am going to set my window to go from x values of 0.1 to 8.1, since I'm really looking from 0 to 8, and I'm actually going to make this a negative 0.1. I try to do that so I can see the y-axis. And I'll set the y scale to go from negative 10 to 75 and see how that works. So I graph these two functions. So here they come. And I'm going to look for that intersection point. So after they get done graphing, I'm going to do second function calc. I'm going to look for the intersection point. There's my first curve. There's the second curve. I'm going to move my cursor a little bit closer to the intersection point. Hit enter. And there it is. So 6.204 is where E of t is equal to L of t. And that is my critical point. That means then if I'm looking for where this function is maximized, I am going to check the following values. I am going to check, let's see, scroll back down here. I'm going to check where t is 0, t is 6.204. That was my critical point. And at 8 at the endpoints. And so I'm going to find f of t. Now, when I find f of t here, of course, f of 0 is going to be a constant in both of these, so it really doesn't come into play in terms of determining when the maximum number of fish are in the lake. But when I integrate from 0 to 0, that's going to be a 0, of course, and I'm assuming no fish are in the lake. This one here at 6.204, we can integrate the E of t minus L of t, so that's what we'll do on the TI-84. So I am going to go to Math 9. Let's get out of here. We'll do a Math 9, and we are going to integrate from 0 to 6.204. We are going to do y1 minus y2 because we're talking about E of t minus L of t. So y1, take away y2, and we see what we get. And the answer is 135.105. So we'll record that. 135.105. I'm now going to integrate from 0 to 8, so I'm going to go back and grab this function and change my limits to 8, from 0 to 8. And what do we get? 80.920. So this ends up being 80.920. So it looks like in this interval from 0 to 8, this is going to be my maximum number of fish that are in the lake. I will make that explanation here with words. I'm going to say from 0 to 8 inclusive at t equals 6.204 hours after midnight. These are hours after midnight. There is when there is a maximum number of fish in the lake. Now the problem originally asked us here, part C, at what time is the greatest number of fish in the lake? And so we're only giving the time here as our answer. I'm not going to say that the maximum number of fish is 135.105 because I don't know how many fish were in the lake at midnight. Presumably there are fish in the lake at any given time, and I do not know what the initial condition was at midnight. But again, as I said, whatever it is, that number would have been added to each one of these answers. And so I still can use this method to find my maximum number of fish. And when that, or I can use it to find when the maximum number of fish would occur, but I really don't truly know the number of fish at that particular time. Part D is asking us, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? Explain your reasoning. Well, if f of t, as we defined it in the previous part, is instantaneous fish in the lake, instantaneous number of fish, instantaneous number of fish, that would mean that f prime of t is the rate of change of the fish. And if I'm going to know whether that rate of change, f prime of t, is increasing or decreasing, I'm going to have to use the second derivative. And so I need to know what f double prime of t is. Well, f of t from the previous problem was really, it was, or I should say f prime here, it was really just e of t minus L of t. All right, so that means then that the second derivative would be e prime of t minus L prime of t. I want to know then if this second derivative is positive or negative at time t equals 5. So I need to know what e prime of 5 minus L prime of 5 is. And of course, if that quantity, that second derivative quantity at t equals 5 is positive, that means that the rate of change of the fish in the lake is increasing. If it's negative, it's decreasing. So what I'm going to do here is I'm going to go to use Math 8. And I am going to take the derivative of y1, which was my e of t, and I want to know what that value is at 5. And I am going to subtract from that Math 8 the derivative with respect to x of y2, which was my L of t function. And of course we're evaluating that one also at x equals 5. And we get an answer of negative 10.723. And so we have found that this is negative 10.723, and this is fish per hour, right? Fish per hour squared. So that means at the exact moment that t is equal to 5, the rate of change of the fish is decreasing at 10.723 fish per hour every hour. But we will answer this question by saying that the rate of change of fish in the lake is decreasing at t equals 5 because f prime of t is decreasing. Okay, the other way that I could have explained that is to say that because f double prime of t, the second derivative of f of t, is negative. But I'll just say it that I have determined that f prime of t is decreasing at that particular moment in time. All right, so that wraps up FRQ number 1. I hope it was helpful.